Hello, I'm Alex Lidar, CEO and co-founder of Efficient Power Conversion. And today at Bodo's Wide Bandgap event, we're going to talk about GaN integrated circuits and our roadmaps. So one of the first things we need to ask is what problems are we trying to solve? And then we'll talk about how the platform is evolving. GaN technology is a fast evolving technology, and the ICs are also fast evolving independent of the platform. We'll look at both. And then what do we expect going forward? So what problems are we trying to solve? Well, like any good power system designer, we're trying to improve efficiency, size and weight, certainly cost, and EMI. We'll touch on all of these today with our ICs and our IC roadmap. But first, let's look at a little bit of history. So shown here is a graph where the vertical axis is the theoretical on resistance of a 1 square millimeter device versus its breakdown voltage. And this shows you the basic capability of a technology based on a material. In this case, silicon, where you see the black diagonal line. That is the best you could ever get from a silicon power device. The blue line is for gallium nitride. And you can see that they're very far apart. As a matter of fact, gallium nitride is about 6,000 times better than silicon. Today, you can buy silicon power MOSFET discretes on that silicon limit. Now, about 10 years ago, EPC introduced its Generation 4 technology, and that was 600x away from the gallium nitride limit. And we started building integrated circuits on that technology. And let's look at some of those. So, since gallium nitride makes lateral devices very efficiently, shown here, small lateral GaN device where the gate, the drain, and the source are all on the same surface, you can actually put multiple power devices together on the same chip. And here you see second device, and they only interact if they're connected through the metal layers. That allows you to put both a high side and a low side power device on the same chip, something that's very difficult to do in silicon, and certainly at higher voltages, not practical. This is a monolithic half bridge. And let's look at what advantage you gain from putting them on the same chip. So here's that monolithic half bridge, and I've drawn a circuit on the right of it, which actually includes all of the parasitic inductances that you might experience if you had a couple of discrete devices, a high and a low side FET. And if you put them together like we have on the left-hand side, this device was introduced 10 years ago, then you eliminate this power loop inductance between the two devices. Well, it seems like a small thing, but it actually has a big impact. Now let's take a look at that. This is a chart comparing the efficiency gained in a 12 volt in to 1.2 volt out and 1 megahertz buck converter. And actually it shows you the evolution of the technology from generation 1 to generation 2 to generation 4. And these are all discrete implementations of this buck converter. But when you get to generation 4 and you stick the two devices onto the same chip to make a monolithic half bridge, you gain even more. And that's through the elimination of the power loop inductance. So these are actually a comparison of devices with the same on resistance. And the difference is the discrete devices are discrete and they're driven by a third chip that's a driver IC, whereas the monolithic is driven by that same driver IC, but the two chips are put together on one substrate. So big difference. Now let's look at another way of integrating. So here we have our power device, and since it's a lateral device, it's very easy on the same chip to add low power, low voltage, logic and analog devices. Here's a cartoon showing you how that's done on the same chip. And now let's look at when we actually did it for a new device. This is an integrated circuit. It's 1.5 square millimeters, and it was designed specifically for time of flight measurements, indirect time of flight specifically, for light detection and ranging systems or Lidar systems. The left-hand side of the chip is a driver IC, and on the right-hand side you see the power transistor. The block diagram looks like this. So we take a FET and we put a driver on it. But in so doing, we also eliminate two key parasitic inductances, the common source inductance and the gate loop inductance. In Lidar systems, speed is everything. And those two inductances are key barriers to gaining maximum speed out of your system. Now let's take a look at what that means in terms of a circuit. Here's that same IC. It's a 40 volt 10 amp device. It's 1.5 square millimeters using our Gen 4 technology, and the waveforms here are showing it clocking at 100 megahertz. Which is a very good frequency for short distance time of flight measurements, say a meter or 2 meters away. It's putting in about 25 volts in this case and 10 amperes out. Now let's take a look at the evolution of this platform. I showed you before the Gen 4 technology and how it was 600x away from the theoretical limit. That time of flight IC was built in Gen 4 technology. But now, about 4 or 5 years ago, we introduced a Gen 5 technology, which was twice as good, 300x away from the GaN limit. And now we are bringing out integrated circuits using that technology. Here's that same chip I showed you on the Gen 4 technology, and here is the next generation on Gen 5. The EPC 21702 takes the input voltage from 40 volts to 100 volts, triples the output current to 30 amps without a loss of resolution. We can still clock this thing at 100 megahertz. It's 3 square millimeters, but as you can see, it's far more capable and can see about 8-10 times as far without losing resolution. Now let's go to the next level of integration. Here we have the power device with its analog or digital circuitry on the same chip. We also showed you how we can integrate a high side device. We can also put low voltage logic and analog on the high side, and then we need a level shifter to communicate between the two. This forms a fully integrated power stage. The initial integrated power stage in our Gen 4 technology was launched about 2-3 years ago. This is a block diagram. You can see the power devices in a monolithic half bridge with their own drivers, level shift, a sync boot to drive the high side gate voltage above the rail. You have input logic, you have some protection circuits, but it requires simple logic level ground referenced in, and you get high power out. This is that chip, the EPC 2152. It's 35% smaller than discrete implementation. It has half the components. It's easier to design with because all you need is logic in from any kind of a microcontroller and you get power out, and it has better efficiency. This is the just the circuit of the output side, the monolithic half bridge side, but it shows you that we have actually been able to eliminate many more of the parasitic inductances that slow down a device and generate EMI. And let's take a look at what that means in terms of overall system performance. Here we have a buck converter, 48 volts in, 12 volts out. In this case, running at 1 megahertz, the solid lines, 2.5 megahertz, the dotted lines. The green is the monolithic half bridge. The blue is discrete implementation, discrete GaN devices with the same on resistance driven by an external driver IC. And much like we saw in the monolithic half bridge, there is a tremendous improvement in efficiency by putting everything together onto one chip. Look at that extra efficiency. And this is for devices with the same on resistance. So we picked up area, we picked up efficiency by putting it all together. There is certainly a lot easier design and lower overall cost. There's also an improvement that can be gained from this monolithic power stage in high-frequency brushless DC motor drives. Now, in a brushless DC motor drive, you basically have an inverter. You take a DC signal in, you create AC waveforms, typically 3 phases of AC waveforms to drive the motor. And this is showing you a traditional brushless DC motor drive. You can see the AC waveform drawn a little yellow oval around a segment of that and amplified it down below, so you can see the phase current for this single phase out of a 3-phase brushless DC motor drive. You can see the input voltage, you can see the input current. This is running at 20 kilohertz, and we had to use a 500 nanosecond dead time because it's a MOSFET drive, and that means that you've got to wait for the internal diode to recover. So you have to put in dead time. This dead time creates distortion. I think you can see that in this AC waveform. We've also put input filters on this one because it's needed. There's an input inductor and input electrolytic capacitors, which you can see down at the bottom. This is a 36 volt DC in 5 amp RMS per motor phase current system. Now, we built the same system, but this time with our monolithic power stage and run it at 100 kilohertz. And because it's GaN, it doesn't really require any dead time, but the limits of the microcontroller mean we could crank it all the way down to 21 nanosecond dead time without any problems. A few things stand out. First of all, we were able to eliminate the input inductor completely. And because of the high frequency, we're able to replace the electrolytic capacitors with ceramic capacitors. Anybody who's designed with electrolytic capacitors know that they're large and not very reliable. So this is a big advantage. And it doesn't take very many of them, only 44 microfarads worth, as opposed to 660 microfarads with the 20 kilohertz version. Another very important thing to note, there are no wiggles from the dead time, and take a look at the amplitude of phase current, input voltage, input current. All are lower in amplitude than the one on the left, and that's saying that it's generating less transients, less noise. So if you pass EMI on the left, you'll certainly pass it on the right. Now let's look at the overall impact on motor drive efficiency. Here we're comparing that same inverter in the center column to the GaN inverter on the right-hand column. The two of them actually have the same overall inverter efficiency. So if you measure the input to the inverter and the output to the inverter, both run around 98.2 to 98.5% efficiency, although the GaN inverter is running at 100 kilohertz. Well, what does that 100 kilohertz buy you? Well, quite a bit. So for example, if you measure the total system efficiency, it's 10% higher with 71.8%. And the reason is that by eliminating the dead time that's required for the MOSFET recovery, you actually eliminate a 6th harmonic in the inverter waveform, which generates both acoustic noise in the motor and it generates a counter force 6 times every cycle. And that counter force means that you don't deliver power to the shaft. So whereas the efficiency may be the same for the inverter, the total system efficiency is significantly different, and it's also quieter. Plus, you've reduced the cost and size of your input filters. No input inductor and a much reduced input capacitor, and it's ceramic instead of electrolytic. So you've gained quite a bit in this motor drive, and imagine a drone or an e-bike, how important these kinds of improvements are. Much like with the Lidar IC, we've been able to take it to a further generation. So our first embodiment shown here, the 2152, 3 years old, we've now gone to a 5th generation device, the 23102. We've put it in a package. It's now 100 volts, half the on resistance, twice the output current, and it's in a very convenient 3.5 by 5 millimeter PQFN package. So if you have any troubles with assembly with the smaller generation 4 device, this should solve all that problems. There's much bigger clearance between the various terminals in the device. There are other improvements that we're inputting along with our upgrade to Generation 5. Over the next year, you'll see 100% on capability for our devices. We'll see multiple floating wells, shoot-through protection, current sense, temperature sense, and many more things that we can add as we evolve our IC technology and capability. But probably most important is the basic underlying platform. Let's go back to this chart. And there's our Gen 5, 300x away from the theoretical limit. And today we're launching our Gen 6 platform. And it is twice as good. And it's 150x away from the GaN limit, which means there's still room for improvement. Let's compare it against other GaN competitors. Here we're comparing against our own Gen 5 platform. We're comparing against GaN Systems, InnoScience, and Infineon. And we're comparing our Gen 6 in 3 key areas that determine performance and cost. First of all, on resistance times area. That drives cost. That tells you the die size for a given power handling capability. And our Gen 6 is 4 times better than Infineon, 4 times better than InnoScience, and 5 times better than GaN Systems. How about radius on times QGD? That drives hard switching performance, or the losses at higher frequencies. And as you can see, it's 10 times better than Infineon, 3 times better than InnoScience, and 3 times better than GaN Systems. radius on times QoS, that drives soft switching performance, very important in resonant circuits or LLC DC to DC converters. And as you can see, it's about 50% better than Infineon and GaN Systems, and almost 3 times better than InnoScience. So by far and away, the best performing platform that you can buy. And here's a comparison in performance with the older Generation 5. Again, Generation 5 was the state of the art until Generation 6 came along. And we're comparing against 2 devices, one that's twice as big but the same on resistance, that's shown in blue, the EPC 2218, and one that's the same size but twice the on resistance, the EPC 2204, and they're both being compared against our EPC 2619 Generation 6 device shown in green. So the Gen 5 are our latest Gen 5 Plus devices, and you can see the advantage that you get with the new Generation 6. Even though it's half the size of the blue EPC 2218, it has much higher efficiency and can conduct higher current for the same case temperature. So you get more than 2x higher current density in this 48 to 12 volt 1 megahertz buck converter. And let's look at light load efficiency. Light load efficiency, the Gen 6 performs just as well as the EPC 2204, which has the same die size but twice the on resistance. So you basically have 2x lower switching losses. So here's the journey on a timeline. Our Gen 4 about 10 years old, and then we built a bunch of ICs, starting off with simple monolithic half bridges and then evolving to parts with drivers and monolithic power stages, all using a Generation 4 platform. And then over the years, we generated a new platform, Generation 5 and Generation 5 Plus, and now we've started to evolve our IC technology. So we have Generation 5 chips, both power chips for monolithic power stages, as well as soon multi-well power stage devices. And then we're launching today our Gen 6, and in 2024 we should have that also on our IC platforms, giving an additional boost to the performance to these power stages, these time-of-flight ICs, as well as many other. And by then, we'll also have our Generation 7. So what are the benefits from integration? I hope they're clear now, that you get higher efficiency, you get lower EMI, you have a lower component cost, a shortened time to market, and saving precious PCB area, which all combined gives you a lower system cost. To learn more, come to our website at epc-co.com and buy our new book, GaN Power Devices and Applications. Thank you.